Hey guys, welcome to this video. So in this video we're going to talk about different kind of classification metrics. So in the previous video we talked about a binary classifier, that is the logistic regression, and there are a lot of metrics we use to understand whether a particular classification model is performing good enough or not. And in this video we exactly going to talk about different kind of metrics, when to use what, and then we'll be concluding our discussion by a Python implementation. So to understand what you are actually interested in, so when I have any kind of a classification model, let's say we have a binary classification model, right? So we have the y, which is the actual value, and the y predicted. Now when I say I wanted to understand how much my model is actually performing good, so let's say I have ones, which is let's say 10 times, and 0, which is let's say 8 times, and my model is saying 1, let's say 8 times, and 0, let's say 6 times. Now if you consolidate this particular numbers, is basically what enable us to understand how much my model is actually performing, or the evaluation of a particular model. Now any kind of a classification model is actually, the discussion starts with something called as a confusion matrix. Now confusion matrix is a specific tabular layout that allows the visualization of the performance of any kind of a classification algorithm. Now let's say, actually how we can show a confusion matrix. So for our discussion I gonna talk about a classification, a binary classification model. So let's say in this side we have the predicted, and this side we have the actual, and let's say it's yes, it's no, it's again yes, it's no. Now what I actually we mean is that, let's say we have a 1 here in the actual, and we have yes in the prediction. That means the actual is also yes, and my prediction is also yes, which is basically exactly this case, this scenario. So in this case it is 8, where it is the actual is also yes and the predicted is also yes. Now the another case, that is the when actual is yes but the prediction is no, that is my in this case, like what we say is, actual is yes but prediction is no, so it is 2. Now actual is no but we have predicted as yes, that means it will be the two scenarios. And finally we have both actual as no and the prediction as no, which is basically the 6. Now this term can be individually can be named. So this is basically your true positive. This is what we call as false negative. So false negative because the actual it was yes, but our model has predicted it as negative or no. This is your false positive, and finally we have true negative. Now if we just convert this for particular confusion matrix, then how it will look like is basically something like this. So again, this is the prediction, this is the actual. Let's say this is true, this is false, this is true, this is false. So this is my true positive, this is false negative, this is my false positive, and finally this is the true negative. So this particular the tabular layout is what we call as a confusion matrix. Now confusion matrix doesn't actually gives you any particular way to evaluate directly, but it just gives you the numbers by which, by these numbers you're gonna use other metrics which can be can tell us how much our model is performing good enough or not. Confusion matrix. Now using the values or the numbers in the confusion matrix, we can first do the the first metrics we actually use frequently is the accuracy score. The accuracy score is nothing but the all the number of correct predictions divided by all kind of predictions. So the correct predictions, if we look into, is the true positive and true negative. So it will be true positive plus true negative, and summation of all the values inside the confusion matrix. So it will be sum of true positive, true negative, false positive plus false negative. So if we use the values we have here, it will be 8 plus 6, which is 14, and we have 8 plus 6 plus 2 plus 2, right? So it will be 14 divided by 18. So this will be almost around 90% accuracy, right? So if we have a model and we are getting around somewhere around 80 to 90% of accuracy, and we can say then our model is performing pretty well, and we can call it a day. But here comes a catch with accuracy. In most of the case, accuracy is good enough, and we can say our model is well, very good. But the issue comes when we have let's say let's take a situation of credit card or a credit card fault, a kind of a transaction is happening, and we have a model which can predict whether the transaction is actually some kind of a bad or good or something like that. Now the problem is that if we look into the data set, so data set will have the majority data in which the transaction was okay, transaction okay. So let's say the data set size is around 100. We have 100 rows, and not okay, not okay, yeah, it will be very less. So let's say it is 90 and it is 10, right? And the model is out of this 90, let's say it has predicted 80, and in this case it has, let's say, predicted 2, right? So let's take the accuracy score. So the accuracy score is 80 plus 2 divided by this 100, and 82%, right? So we can say our model is actually 82% accurate, and we can say our model is very good, and we can deploy. The problem comes in here, in the elephant is actually, or the devil is in the details, right? So the detail, if you look into this here, what are the true sorry, yeah. So what will be the the false negative here? So false negative, that means which were true, where transaction okay, but it has flagged as not okay. So that is 10. And not okay, that means it was a some kind of a bad transaction, but the model has flagged it as okay transaction. So this is as false positive as 10. Now if you look into this, sorry, not 10, it is 8. Now if you look into this, we have total observations 10, out of which my model is not able to get this 8 transactions properly. So whether my model is good enough? No. So in this kind of situation, the accuracy score is not a good measure. And that is why we have the other measure, in which we also take into consideration with respect to the false positive and false negative terms, right? And here we have the second metrics we call as the sensitivity. So sensitivity can also be called as a recall. So sensitivity can also be called as recall, and wait a second, yeah. So sensitivity can also be called as TPR, which is true positive rate, right? And the formula is basically your true positive divided by the sum of true positive plus false negative. So this measure, or this particular metrics, is basically measure of the trueness, or how much our model is spitting out true values. And if you look into, if we just use these values over here, it will be pretty high for this kind of model. So the true values are here, let's say for this one, we have 80, 80 plus false negative, which is 10. So 80 by 90, so this is almost equals to 90%. The TPR or the recall or sensitivity value is 90%. Now let's also check the something called as a specificity. So specificity is more of a measure of the negativeness. So specificity is formalized true negative by the sum of true negative and the false positive. So true negative in this case, if you look up here, we have 2, 2 plus the false positive. So the false positive is 8. So 2 out of 10, that is 0.2 or 20%. So now we can have a better understanding that how good our model is performing. So as you can see, the negative characteristics or the how we can measure the negativeness of uh, the model is pretty much bad. We can see it is able to capture the positive side of it, but the negative side is not good enough. And this is actually happens more often in case the data set is not balanced. You have certain minority classes in your data, and the model is the metrics, if you use just the accuracy, is not a good measure. We do not have a true picture of how the model is, and that's why we need other metrics to understand properly. And so yeah, so specificity is the basically the trueness. Now the specificity is basically 1 minus the false positive rate. So we have another matrix called as false positive. We just just a like a different kind of an representation of the specificity, but it is basically deals with the how much the false representation of the the target variables are calculated. So false positive, if we just do it like this, it will be fp divided by tn plus fp. So we have covered the accuracy, sensitivity, recall, and specificity. Now we wanted to understand how much, let's say, the precision. So precision looks into more of the out of all the truths, how much actual truths are being captured. So this will be false positive. Now the all the truths that or the true values that the model is spitting out of it, out of that how much of them are actually true, so that is your precision. And after that, finally we reach to something called as a acha. So after this we actually want to discuss something called as a f1 score, right? So so we have the picture available from the sensitivity about the whether the model is performing from the positive side, and we also have the negative side picture from the specificity, and then we also have the picture of how much of the true values out of all the truths are actually true. Now to convert them all or put all in one place, we have the f1 score. So f1 is basically a harmonic mean. It's a harmonic mean of recall and my precision. Now what it does is basically that it actually brings the both the pictures from the recall and the precision, and combines them together and puts you a number in which you get actually a combined picture of the precision and the sensitivity, right? So the formula will be looking something like, right? So this is the f1 score. Now as you can see that the f1 score actually performs really well when the recall and precisions are actually almost very similar, or the values are comparable. Now the sixth, we have something called as the AUC ROC. So the ROC full form is region operating characteristics, right? So this ROC is nothing but is actually a curve, we can determine, by the help of which we can determine how good our model is. And what it does is that, if I just try to plot it up, so in the y-axis we have the true positive rate, and in the x-axis we have false positive rate. And let's say we just draw a line which is at 0.5. So this is the 0.5th line. And what it does is that by the help of this curve we can understand how good our model is. So let's say if our model is performing something like this, that means the curve is very much close to the TPR, that is the ROC is towards the upper left side, and that means the model is very good. And if ROC is at the 45, which is basically the 0.5th line, then our model, so model is basically underdetermined. It doesn't know whether the particular y belongs to the 0th class or the 1th kind of a class. So in other way, we can say that the best possible choice is that we do not have a model where it lies on this 0.5th line. Now the AOC is nothing, is just the area under this curve. So if we have, we used to do the summation of the area. So the total area under this ROC curve is the AOC. So AOC, if you look into it in this way, AOC, if this curve is very much close to this and it goes to almost as 1, so AOC value will be tending towards 1. So as the AOC value increases, the model is better. So this is the thumb rule. Means the more the area we have, the quality of the model is actually getting increased. Now the question that remains is that how we have so many metrics, we have different situations in we take different kind of metrics. Then the question is that how we can understand what is the optimal situation. So the optimal situation, if I say so the optimal situation is when we have good accuracy. So by good accuracy, there is no value exactly in which we can know, we can say that this is a very good accurate model. But for the sake of our conversation, let's say it's greater than 0.7 or 70%. We have decent recall around 0.7 to 0.8, and we have a decent specificity. So same around 0.7 to 0.8. Now if these three conditions are met, we can say our model is quite optimal situation, or it is more generalizable. There is no like a bias that it can actually predict good. In case of the prediction being one, it is better, but while dealing with a minority class, it's not good enough. So if we have this kind of situations, I mean, if this kind of situation, then this is the optimal situation in which we can say that our model is good enough. Now there is also a question that when a particular metrics will be taken into, the metrics which you want to be more. So let's take a situation. Let's take a corona virus detection model, right? So let's say we have made an AI model which can detect, by the help of, let's say, X-ray of chest, whether a particular patient has COVID or not, right? So in this kind of situation, we wanted a model in which the false positive, if it is higher, we do not care, but the false negative value should be as low as possible. Because if you see the situation in which the model say it's, it's a covid positive, so there can be further investigation they can do, rt-pcr or things like that to confirm whether the patient actually has covid or not. But let's say the model says it's negative, so all the steps in which we can actually confirm doesn't happen, and as a result a person who has a covid virus will be going out in the crowd and it will be spreading more, right? So in this kind of situation we wanted our or the trueness of the model more. In this case the recall is the metrics we are more concerned with, so we want to increase our recall score in this kind of a model. Now the same, if we have, let's say, another situation, let's say we have made an ai model, which, let's say, it says that, let's say it's a judiciary model. That means you give inputs as the all the documents, allegations and stuff like that, and it says whether a person is guilty or not, right? So in this kind of situation we wanted a kind of a model in which the innocent person, so the innocent person shouldn't get a sentence, no sentence for innocent person. So in this case we wanted our, specificity to be more, to be pretty high, because we wanted, even though we have some person, getting, I mean, even though he is a criminal, he is going out, so there is a chance that, the other person, the who has done the complaint, he can go to the higher court and appeal. But if an innocent person is going to a jail, that is not a very good situation for judiciary. So in this kind of a situation we wanted specificity to be more of the model, right? So we have actually, covered most of that, underlying topics of different metrics, when to use what. We have discussed about how we use this kind of a score, for imbalance kind of a data set. Now let's do this in python and understand it more. Hey, so we have done this, the classification problem with respect to the, in the previous video, we have used the breast cancer data set. So what we're going to do is we're going to use the same code and we try to understand the different kind of metrics available and see the values. So let me just quickly run the sheet. Cool. So we have run the sheet. So let me import the all this discussion. It starts from confusion matrix. So let me first get the confusion matrix, right? So we have the confusion matrix, and we need to give this white rest, I mean, no, the white true and the white red. Here we have, the confusion matrix. So in sklearn, the the representation is pretty much reverse. So this is basically my, the true negative term and the false negative, all this kind of, so it's reverse. So what we can do is, we can actually try to ravel this. I think I have this over here. Hmm. Right. So now we have, true negative, false positive, false negative and true positive values. So the first thing we will be doing is accuracy score. We also have this accuracy score implemented here. We can directly use that. We have the white test and white red. So our model is around 94% accurate, right? And I believe that, we do have our data set as something like a balanced data set. But anyways, for our test experiment, we can actually go ahead and do the other metrics. So let me first get the recall. So recall is my true positive divided by, sorry, positive by false negative. Let me do one thing. Let me just create a function and get metrics, and I pass this values here itself. Test y ret, and call this here inside this. So I got recall. Then I want the sensitivity VT, which is true negative by true negative plus false positive. Then we have the precision. Precision is true positive plus false positive. And we can also have the FPR, which is 1 minus sensitivity, right? So let me return these values. We have recall, we have sensitivity, we have sorry, precision, and we have PR. So get metrics, and let me just pass the same values here. Or we can actually show something like this. So this is my sensitivity, precision, and the FPR. So get metrics, and the recall is around 92%, sensitivity is 97, precision is 98, FPR is obviously the negative, the negative rate of it, which is 0.023. Now we have these numbers. How not? Why not? We can also plot this up. So inside sklearn, we do have the ROC AOC score, and as well as the curve value, right? Let me also just call matplotlib. So what we can do now is have this ROC curve value outside. So this ROC curve method, it spits out three values: the FPR, the TPR, and as well as the threshold. So we are only interested in the FPR and TPR, and threshold value we do not need right now. So let me just go ahead and get this. So we have FPR and TPR. Now what we need is we need to plot this here, as the x-axis will be my FPR and the y-axis will be TPR. And let me just also, yeah. So as you can see, like I actually done in this particular notebook, that we have this kind of a curve, and as you can see, the same is actually getting reflected in the AOC, in the ROC curve as well. Now we wanted to get the AOC score, so let me just call the ROC AOC score. So the same thing we need to just pass to it. As you can see, the value is very much closer to 1, and this is actually very good model. The reason being that the coverage or the area under this particular curve is pretty much close to 1, hence our model is performing pretty well. We have the values for the recall and the precisions at in a pretty much in a good level, which means that for both the classes, it's not like it's behaving better for one particular class and not good for another class. Moreover, our model is our data set is also balanced, so that's why we have the scores pretty much in under the same level. To another thing we also can do is the F1 score. So the F1 score is, I can just go over here. Like I said, it's a harmonic mean of the precision and the recall. Right. So the values are pretty much very much same or in the same level. So as you can see, all the metrics we have used, the values are very high. Our model is good enough. But the same can, if we have any kind of a imbalanced data set, we'll be seeing the values for the, let's say, if the model is having very low values of zeros, in that case the specificity values will be very less, right? So yeah, so that's it for the video. And do let me know your comments, if you have any confusion or you want me to do a deep dive on a particular kind of a topic. Let me know in that, and thanks.